So we are going to talk about the Bohr's atomic model. This is a very famous atomic model because it's very useful and very applicable. Most of the calculations that are performed under atomic structure are based on the same model. Okay, so looking at this diagram, it basically summarizes the things that we need to know about Bohr's atomic model. So according to Bohr, basically an atom is made up of a small nucleus, which is of course positively charged. As you can see in our diagram here, you're able to say, if you look at this nucleus, it's very, very tiny. So that dot that is there represents that there is a positive inside there. That's what the Bohr's atomic model tells us. It also tells us to say that it is of course surrounded by the negative electrons moving around. So again, if you look at the diagram that we have, so these are made up of electrons. That's what Bohr's. So they are actually, the nucleus is surrounded by the shells made up of electrons. And then the other thing that we'd have to know is that the electrons that are located away from the nucleus has got more energy as compared to the ones that are near the nucleus. So that emphasizes on the aspect of the energy levels. Okay, these shells are also known as the energy levels. Sorry. So the ones that are closer to the nucleus have got lower energy. So in short, for example, this is bigger, is smaller than, has actually more energy than the one that is smaller inside there. That's what Bohr's model tells us. So in summary, or more in detail actually, if you look at these postulates, that's what they tell us. Okay, so I'll read through. The first one says in an atom, electrons, of course, electrons are negatively charged. They revolve around the positively charged nucleus in a definite circular path called orbits or shells. Okay, so that is all just talking about the diagram that is there. Okay, and then the second postulate is that each orbit or shell has a fixed energy, and these circular orbits are known as orbit or shells. Okay, the third one tells us that energy levels are represented by the integer. So we know what an integer is, right? Okay, so the first one is represented as 1. The second one, 2, as you can see on our diagram there. So those ones are known as the quantum numbers. So we'll talk later about basically how you get to look at the calculations to deal with the quantum numbers. Okay, so that integer n represents the energy. Okay, so the bigger the integer, the bigger the energy of that energy level. Okay, so this range of quantum numbers starts from the nuclear side with n is equal to 1, having the lowest energy level. Of course, we understand that. We say the one that comes immediately after the nucleus is actually has got lowest energy when you begin comparing with the other energy levels. So the bits n is equal to 1, 2, 3, and 4 are assigned letters. Okay, K, L, M, N, shells. So the first one is called, the n is equal to 1 is called K. So you're able to remember that. So, and when an electron attains the lowest energy level, it is said to be in ground state. Okay. So an electron with the lowest energy is said to be in the ground state. The electrons in an atom move from the lower energy level to a higher energy level by gaining required energy. And of course, the opposite is true. What that tells us is if you have an electron in the first energy level, for it to go to a higher energy level, we've said the one that is smaller or the one closer to the nucleus has got lower energy. So for it to move to the one that is outer there, it has to gain energy. That's basically what the last point is saying. And of course, the opposite is true. For an electron to move from the outer energy level to go to one that is inner or closer to the nucleus, it has to lose energy. Okay, so all that can be summarized by the simple calculation that we're going to be dealing with when you begin studying the transition of electrons. So you look at the use of this formula. Okay, so where you talk about the final energy level and then subtract the initial. So that basically summarizes everything that you basically get to deal with here. So let's say you have a transition of an electron from the fourth energy level to the second energy level. You would have to substitute there. So that would be 4 squared as a, or actually the final one in this case, as we are going to is going to be 2. And then the initial one was 4. So you have 1 over 4 minus 1 over 16. So you understand that 1 over 4 is bigger than 1 over 16. So in the brackets here, if you get to subtract, you basically get to have a positive solution multiplied by the negative that is there. it remains a negative. So which tells us to say that the negative represents loss in energy. Okay, so the opposite is true. If it was moving from 2 going to 4, you'd get a positive answer, telling to say the electron had gained energy. And then, of course, in conclusion, you can talk about the limitations of Bohr's model. Okay, so these are the limitations of the Bohr's model of an atom. It failed to explain the Zeeman effect. It failed to explain the Stark effect. It violates the Heisenberg uncertainty principle. So if you don't know about that, you can watch our video about that. You'll be able to understand what Heisenberg uncertainty principle tells us. Of course, to give you an idea is if you basically know the position, it's very difficult for you to know how fast it's moving. Okay, so it's either you know much about its position or you know much about its velocity or its momentum. So it could not explain the spectra obtained from the larger atoms. So that's it about the Bohr's model of an atom.